Hello everyone, welcome to BYJU'S Exam Prep, the most comprehensive preparation app for all exams. Good morning all of you. Am I properly audible and visible to all of you? Please let me know once in the chat box. Yes, and guys, do like the session and share with your friends so that we can have maximum students and they can take the benefit of this session, because this is formula revision series, and here we are going to revise all the important formulas that you need in this BARC 2022 CS exam. So guys, quickly just confirm once, am I properly audible and visible? Please let me know once. Then we can start this session. Okay. So here in this series, we are going to cover the formula, all the formulas, important formulas for computer science. So before starting, let me introduce myself. My name is Anshul. I have 2+ years of teaching experience. In GATE 2020, I have secured All India Rank 294, cleared ISRO and IELTS exam, mentored more than 1,000 students as of now, and these are my area of expertise. Okay. And guys, if you want to connect with me, you can join this Telegram group. This is the link. So I will be sharing the PDF also. No, Gotham, MSQs are not there in BARC. So I will be sharing the PDF in this group. So you can connect with me. You can, if you need any guidance related to your preparation, then also you are most welcome. And if you need the PDF of this class, I will be sharing the PDF just after my session. And if you have any doubts, you can ask your doubts in this group as well. So this is the link, you can join. Now, so there is one strategy workshop that BYJU'S Exam Prep is going to conduct tomorrow at 19th on 19th Feb at 8 p.m. Okay. So those who are aspiring for GATE 2023, so don't miss this session, because this is going to be very helpful on how to prepare, how to approach your preparation for GATE 2023. Okay, MSQs are not there, Gotham. MSQs are not there. Yes, we are providing mock test also. WebHub, we will be providing mock test as well. Okay, right. So, and this is the most important session, guys. Today at 9 p.m. I will be conducting this session for computer science. So basically, I will be providing you the rank prediction for this GATE 2022 computer science exam. So based on your expected marks, I will provide you the closest range of your GATE rank. Okay, so don't miss this session today at 9 p.m. only on BYJU'S Exam Prep YouTube channel. So, and I would also request you to subscribe and press the bell icon so that you don't miss the notification of this class. Also, I will be sharing the link in my Telegram group today at 9 p.m. Okay. Right, so let's start with the formulas and important points that you need to know. So first of all, we are starting with digital logic. So these are the laws that are very helpful. Identity law. So basically in identity law, what we do, basically if it is A or A, so we are going to get A only. A and A will give us A only. The most important laws that you need in this exam, that is distributive law, because we need distributive law while simplification. Okay, if you want to simplify any Boolean expression, then we need this distributive law. So A and B or C, so we can distribute this AND operation over OR operation. So we will be writing AB or AC. Clear? Similarly, here I will be distributing this OR operation over AND operation. So I can write A or B and A or C. So this is very important. Apart from this, this De Morgan's law is also important. So here A or B whole complement will give you A complement, B complement. AB whole complement will give you A complement or B complement. Clear? Then we have commutative law and associative law. Basically in commutative, we just reverse the positions of the Boolean variables. So here it is A or B, we will be getting B or A. Here it is A and B, we will be getting B and A. Yes, guys, good morning. All your doubts related to this GATE exam I will clear in today's 9 p.m. session, so don't miss that. You can ask your doubts there. Okay, right. So associative law, so here it is A or B or C, so we can write A or B or C, so that is the same. And here it is A and B and C, so we can write A and B first, then and C. Clear? So these are some important laws, and now let's proceed. So these are very important points here. NAND and NOR gates do not follow associative law, but they follow commutative law. This is a frequently asked question, and in 1 mark you can definitely expect this question, that NAND and NOR, they don't follow associative law. You can prove as well by substituting the values, but they follow commutative law. Whereas we talk about OR and XOR and XNOR gate, they follow both commutative and associative laws. Clear? And then we have this simple properties based on distribution law. Okay, let's proceed further. Now here, these are the important things. These are the important things that we have. A minute. So here you can see A complement XOR B, it is equal to A XOR B complement. It is also equal to A XNOR B. And we can also write it is equal to A XOR B whole complement. Clear? Similarly here, A XOR B, it is equal to A XNOR B whole complement, which is also equal to A XNOR B complement, A complement XNOR B. These two are very important properties. Okay, directly questions can be framed on this. Yes, I will be sharing the PDF in my Telegram group, Abhishek. Okay. This is also very important point for odd number of inputs. So if you have odd number of input variables, in that case, both XOR and XNOR will be same. As you can see here, here it is A XOR B XOR C. 3 Boolean variables you have here. Also it is equal to A XNOR B XNOR C. But in case if you have even number of variables, even number of Boolean variables, then they are complement of each other, as you can see here. Here you have even number of variables, both are complement of each other. Clear? But if you had odd number of variables, both are same. So this is very important property. Keep this in mind. Now let's proceed, and now we are going to talk about the number of NAND and NOR gates needed to implement other logic gates. So this is frequently asked question that can be asked. Some expression will be given to you, and they will ask you how many minimum number of NAND gates and NOR gates required. Okay. So here, if we just want to implement any Boolean expression using just NAND gates, so let's say if you want to implement NOT gate, only one NAND gate is required. Similarly, only one NOR gate is required. So this is a kind of quick revision for you. Okay, we are not going to explain you the whole concept. I hope you understand that. Now, if I want to implement AND gates, so 2 NAND gates are required and 3 NOR gates are required. If I want to implement OR gate, 3 NAND gates and 2 NOR gates are required. So you can remember this like this: 1 1, that is for same NOT. Then we have for AND it is 2 and 3, for OR it is 3 and 2. Similarly, if you talk about XOR and XNOR, so here it is 4, this is 5, this is 5, this is 4, just the opposite. Clear? So this order is important. Based on this, you can easily answer most of the questions. Now let's talk about the number of functions. So this is also important when we talk about maximum possible self-dual functions. So what is a self-dual function? Before that, you need to understand what is neutral function. So neutral function, when the number of minterms is equal to number of maxterms, then we call it as neutral function, right? Now if you talk about self-dual function, so there are two conditions for a function to be self-dual. First condition is the function should be neutral. That means number of minterms should be equal to number of maxterms. Second condition is there should not be any mutually exclusive terms present in the expression. Okay. Now what is mutually exclusive terms? So this is 0, 7. Let's say we have 3 Boolean variables. So 8 combinations will be possible. 8 combinations will be possible from 0 to 7. So 0, 7, they are mutually exclusive term. Why? Because if you take the complement of 0, you will be getting 7. How? 0 you can write as 000, 7 you can write as 111. So that's why these two are mutually exclusive terms. Similarly, 1 and 6. Similarly, 2 and 5 and 3, 4. All these are mutually exclusive terms to each other. Clear? So that means there should be only one mutually exclusive term. That means out of 0 and 7, either 0 or 7 should be present. Out of 1 and 6, either 1 or 6 should be present. Similarly, 2 or 5, 3 or 4. So these are the two conditions for a function to be self-dual function. And if we talk about the number of maximum possible self-dual functions, so this is the formula. I hope you can derive it. Okay, how to get it? Let me give you some idea. As you can see, how many pairs we can form. Total combinations will be 2 raised to the power n. N Boolean variables will be there. How many pairs like this we can form? Half of it, 2 raised to the power n by 2. These many pairs we can form, right? So that means we can write 2 raised to the power n minus 1. Now, if each of these pair has two choices, each of these pair has two choices. So 2 into 2 into 2, how many times? 2 raised to the power n minus 1 time. That's why it is 2 raised to the power n minus 1. This will give you the maximum number of self-dual. Now this is also simple. Number of Boolean functions formed over n Boolean variables. So if you have n Boolean variables, 2 raised to the power n combinations will be possible. Each combination out of 2 raised to the power n, we can map to either 0 or 1. So it is going to be 2 raised to the power n. Same for n valued variables. Clear? Now if we want to find out n valued functions, so here we were talking about Boolean functions, but now we are talking about n valued functions. So in that case, if you have n Boolean variables, 2 raised to the power n combination, each combination you can map to 1 out of n. That means you have n choices. So n raised to the power 2 raised to the power n. Clear? These are very important things because in BARC exam, you can expect only 1 mark questions, okay, that you can solve within 1 minute. Most probably within 1 minute, you can solve any question. So these are important things that you can expect. Now let's talk about the adders, half adder and full adder. So this is the circuit for half adder. Sum equation is A XOR B, carry equation is A and B. If we talk about the logical expression for full adder, so it is going to be A XOR B XOR C. This is the sum equation for full adder. Okay, and what is the carry equation? Carry equation is AB plus BC plus CA, or you can write in this way as well, AB or C and A XOR B. If you simplify this, you will be getting this thing only. Okay, so this is the equation of, this is the carry equation for full adder. Now why we are writing this equation, carry equation in this form? So that I can implement one full adder as 2 half adders plus 1 OR gate. Okay, due to this reason, we are writing the carry equation in this way. Good morning. Hi Pinky, good morning. Is it clear so far, everyone? Okay, so let's proceed further. Now let's talk about half and full subtractor. Half and full subtractor. So here you can see the logical expression for the difference is same as the sum equation for the half adder, that is A XOR B. If we talk about the borrow equation, it is A complement B. Okay, this is for half subtractor. Now let's talk about full subtractor. So difference equation will be A XOR B XOR C, and borrow equation is this one. So it is A complement B or A complement C or BC, or you can write in this way as well. Why we are writing in this way? So that we can implement full subtractor in terms of half subtractor also. Okay, I hope it is clear so far. Let's talk about multiplexer now. So here we are talking about 4/1 multiplexer. 2 select lines will be there because multiplexer always exists in this form, right? 2 raised to the power n by 1, 2 raised to the power n inputs will be there, 1 output will be there. And if we talk about this characteristic equation, so we can write it in this way. S1 complement S0 complement I0, or S1 complement S0 I1, S1 S0 I2, S1 S0 I3. So when we are taking both as zeros, I will be selecting I0. When 0, 1, I will be selecting I1. When 1, 0, I will be selecting I2. When 1, 1, I will be selecting I3. Clear? So I hope you can solve the questions based on multiplexer also. Now let's see the ripple carry adder. So sometimes they may ask you a question where you have to find the total propagation delay to add two numbers. Suppose you have 4-bit number A3, A2, A1, A0, and you want to add with the B3, B2, B1 and B0. Now 4-bit numbers are there. So they will provide you, like, you know, n is equal to 4 here. You have to find total propagation delay. TC is the time taken to generate the carry. Tsum is time taken to generate the sum bit. Okay. So here total propagation delay, this is the formula, n minus 1 into Tc plus maximum of Tc comma tsum. Directly formula based questions will be asked. Okay, now let's talk about carry look ahead adder. So in case of carry look ahead adder, these are the important formulas where they can ask you the number of AND gates required and number of OR gates required. So if you know the equation of yes, Pinky, there were very few questions from digital. So basically the paper was not a standard paper, right? If we talk about GATE 2022 exam. So here number of NAND gates is n into n plus 1 by 2, where n is the number of bits, n number of the number of bits you have in the these two numbers which you are adding, and number of OR gates required is n here. So these are the important things from these two. Let's talk about this equivalent logic gate diagram. So here we want to convert binary number into gray code. So this is the thing. Directly B3 will be giving to G3, and then to generate G2 we will be performing XOR between B3 and B2. Similarly, B2 XOR B1 will give you G1, B1 XOR B0 will give you G0. So here also we have written it. Clear? Now the reverse of it, if you have the gray code, and you want to convert it into binary, then G3 directly you can give to B3, then B3 XOR G2, will give you B2, B2 XOR G1 will give you B1. Or you can remember in this way also. Let's say you have one number, let's say 1101. Okay, suppose this is a gray code. So here I can write this most significant bit as it is, and then I can perform the XOR between these two bits, 1 and 1, and this will give me what? 0. Then XOR between 0 and 0, this will give me what? 0. And XOR between these two bits, 0 XOR 1 will give me. Clear? So in this way you can convert. Now let's come to the counters, very important topic. So here in counters they may ask you these type of questions. Let's say you have ring counter. So I hope you know what is a ring counter. That is one of the synchronous counter. Okay, what is synchronous counter? You have the common clock pulse to all the flip-flops present in that counter. So in case of a ring, the output of the last flip-flop will be treated as the input to the first flip-flop. If n flip-flops are present, then it will be mod n counter. Remember this point. In case of ring counter, if you have n number of flip-flops, then the mod of that counter will be mod n. Okay, if you have 3 flip-flops, mod 3 it will be. If clock frequency, input clock frequency is given to you, that is f, so output frequency will be f by n. N you can say number of flip-flops or the mod value. Okay, so that will be the output frequency. Now let's talk about the Johnson counter. So Johnson counter is also one of the synchronous counter, but in Johnson counter the complemented output of the last flip-flop will be given as the input to the first flip-flop. Okay, so if n flip-flops are present, then it will be mod 2 into n counter. If you have 3 flip-flops in case of Johnson counter, mod value will be 6. Okay, if you have 4 flip-flops, mod value will be 8. If clock frequency, input clock frequency is f, then output clock frequency will be f by 2 into n. That means whatever is the mod value, you have to divide that with the input frequency and you will be getting the output frequency of that counter. Clear? Now if I talk about this asynchronous counter, which is also called as a ripple counter. So in case of asynchronous, I hope you know this, that if you have n flip-flops, all the possible states will be present in the counting loop. That's why the mod value will be mod 2 raised to the power n. Okay, so if you have suppose 3 flip-flops, possible states are 2 raised to the power 3, that is 8. So all 8 states will be present in the counting loop. That's why the mod value is 2 raised to the power n. Now if clock frequency is f, output frequency will be f divided by 2 raised to the power n. That means whatever is the mod value, you have to divide the input frequency by that to get the output frequency. Is it clear so far, guys? If you have any doubt, you can ask. Now let's talk about this digital number representation. So here these are the important formulas. If you have an unsigned number with n bits, so the possible range of that number will be from 0 to 2 raised to the power n minus 1. Why from 0? Because it is unsigned, right? We only talk about the positive numbers in this unsigned case. So 0 will be the minimum value, maximum will be 2 raised to the power n minus 1. The range of sign magnitude representation. So whenever we talk about signed numbers, we have three representation. One is sign magnitude, second one is 1's complement, third one is 2's complement representation. So in case of signed numbers, this is the representation, minus of 2 raised to the power n minus 1 to plus 2 raised to the power n minus 1 minus 1. Both sign magnitude and 1's complement, both are having the same range. Okay, same range is there. But if we talk about this range of 2's complement number, in this case, we can represent one more negative number. That's why it is minus 2 raised to the power n minus 1. This positive is same, but this is the difference. Okay, so this is important. 2's complement range is very important. Remember this formula. So let's talk about overflow. So in GATE 2022 exam as well, there is one question from overflow, right? I hope you have answered it correctly, because that was a really simple question. Based on just this shortcut, you can identify whether there is overflow or not. So let's say you are having a 4-bit number A3, A2, A1, A0. You are adding this number with the B3, B2, B1 and B0, right? So if you add this, you will be getting S0 here, S1 here, S2 here, S3 here. Clear? This will generate some carry here, let's say C1, right? This will generate some carry here, let's say C2. This will generate some carry here, let's say it is C in. Okay, C in. And finally you will be getting some carry, let's say it is C out. So now to check whether there is overflow or not, you can perform this C out XOR C in. If it is equal to 1, then it is a case of overflow. Okay, there are other ways also by which you can check, but this is the quickest way, I would say. This is the quickest way. You can find C out and C in for any two numbers, and if it is 1, then it is overflow. If it is 0, it is not an overflow. Good morning, Saubhagya. Okay, now let's talk about IEEE representation. So we have single precision, we have double precision. In case of single precision, we have 32-bit register. In case of double precision, it is 64-bit register. And we have 1 sign bit, 8 exponent bits and 23 mantissa bits in case of single precision. Here you have 1, 11 and 52. Okay, so this is the table. Based on this table, you can easily solve any question based on this single precision. Okay, so here it is. You can see if E is equal to 0, there are two cases for E is equal to 0. When M is equal to 0, it is plus minus 0 depending upon the sign bit. If M is not equal to 0, it is a fractional form. What is the fractional form? This is your fractional form. This is the formula given to you, minus 1 raised to the power s into 0.m into 2 raised to the power minus 126. If E is equal to 255, E is equal to 255, again two cases are there. M is equal to 0, then it is plus minus infinity depending upon the sign bit. M is not equal to 0, it is not a number. It is not a number. Nand means not a number. You cannot represent that number. So we have this combination for it. But if E is lying in this range 1 to 254 and M is anything, then it is implicit normalized form. Mostly the questions will be asked from implicit normalized form. So this is the formula. Minus 1 raised to the power s into 1.m into 2 raised to the power e minus 127. Here in case of a single precision, bias value is 127. So that's why it is 2 raised to the power e minus 127. Now let's talk about double precision. Again, it is almost same, just the difference is of exponent and this mantissa. So here E is equal to 0, E is equal to 0. Again, there are two cases. M is equal to 0, plus minus 0. M is not equal to 0. It is a fractional form, and this is the formula for the fractional form. If E is equal to 2047, E is equal to 2047. M is equal to 0, then it is plus minus infinity. M is not equal to 0. It is not a number. But if E is lying between 1 to 2046 and M is anything, maybe it will be 0 or something else, then in that case implicit normalized form. So this is the formula, minus 1 raised to the power s into 1.m into 2 raised to the power e minus 1023. The bias value in case of double precision is 1023. Is it clear? Is it clear to all of you? If you have any doubt, guys, you can ask in the comment section. Okay, so digital is over. Now we are heading towards the second subject, that is compiler design. So this is also important. Left recursive elimination. Now if you have left recursion, as you can see here, the leftmost symbol you have is A, and which is same as the LHS, so that's why it is left recursion. Now how to eliminate left recursion? So basically, if this is given to you, A derives A alpha or beta, this is the non-left recursive part. Here you don't have any left recursion, so you will be writing first this one, beta, and here the remaining portion where you have the left recursion, the remaining portion you have to write. So A dash alpha here, A dash or epsilon. Clear? So first you have to focus always on the non-left recursive part. So it is beta here. Then you write A dash, and then in the next production you will be writing the remaining portion where you have the left recursion, that is alpha, A dash or epsilon. Clear? So this is how we eliminate left recursion. Now let's talk about left factoring. So in case of left factoring, what is the problem? We have non-determinism present. We have the common prefix problem present, right? So here you can see alpha is present here, alpha is present here. Both are having common prefix, right? So to eliminate this, we perform left factoring. How we can do that? So you can assume like we are taking alpha common and just write A dash, right? Now in place of A dash, what you can substitute? You can substitute a beta 1 or beta 2. Is it clear? So this is how we perform left factoring and we eliminate this common prefix problem. Clear? Now let's talk about LL1 grammar. So how to check whether a given grammar is LL1 or not. So to check whether given grammar is LL1 or not, we have these two rules. If A derives alpha 1 or alpha 2, so you have to find first of this one and first of this one. Take the intersection. If the intersection is equal to 5, then it is LL1. Okay. You can have this type of grammar also where you have A derives alpha or epsilon. Now here you have to find first of this one, alpha, right? Intersection. Here you have the epsilon, so you have to find the follow of left hand side. Because there is LL1, we have to see the next look ahead. So if it is epsilon, we have to find the follow of left hand side and then take the intersection of these two. If it is equal to 5 means there is nothing common between these two, right? No intersection is there. So in that case, it is LL1. Clear? This is the shortcut. Now we have some important points here. A grammar where it is LL1 parsing table has free from multiple entrants. That means if a grammar is not LL1, in that case, you will be having multiple productions present in a single cell if you make the table, okay? But if it is LL1, there will be no multiple productions in a single cell. Now these three are very important points. A left recursive grammar cannot be a LL1 grammar, okay? Whenever there is a left recursion present in the grammar, it cannot be LL1. Whenever you have the common prefix problem, then also it cannot be LL1. And ambiguous grammar cannot be LL1. Ambiguous grammar cannot be LL1. Is it clear so far? Okay, these three are the important points. Now let's talk about the bottom-up parser. So how to find the conflict in case of LR0 parser? We have two types of conflict, shift-reduce conflict and reduce-reduce conflict. If I talk about shift-reduce conflict, when the same state in DFA contains both shift and reduce items. Suppose this is one state you have, this is one state you have. As you can see, there is a shift on a terminal which is X, and there is a final item present. B drives gamma dot. There is a final item or reduce item is present. In that case, this is SR conflict. This is SR conflict whenever you have a shift on a terminal and there is one reduce item present in the same state. Okay, then it is SR conflict. What about reduce conflict? So here you can see, suppose this is one state, two reduce item are present. So two reduce item are present in the same state of DFA, then we can say it is a reduce conflict. If you have any of these conflict, whether SR or RR, you can clearly say that grammar is not LR0. That means that cannot be parsed by LR0 parser. Clear? Now let's say this a simple LR1 parser. Simple LR1 parser in how to find conflicts. So again, let's say this is the one state you have. There is a shift on a terminal X, as you can see here, right? And there is a reduce item present. But in case of simple LR1 means SLR1. So in case of SLR1, if there is a reduce item, you have to find the follow of left hand side. Why? Because we are talking about the look ahead. It is 1 here. In case of LR0, there are no look aheads, but in case of SLR1, there are look aheads. So we have to find the follow of left hand side whenever we have the reduce item. If in the follow of left hand side you have this terminal X, then you can say it is not SLR1, SR conflict is present. Or simply you can write, if X belongs to follow of B, then you can say SR conflict is present. SR conflict is present. Is it clear, everyone? Now what about a reduce conflict? So if you have two reduce items, A drives alpha dot, B drives gamma dot. Okay. Yes, सौभाग्य, error entry ज़्यादा किस में होता है, SLR1 और LR0. See, which one is more powerful? SLR1 is more powerful, right? That means there will be more number of blank entries in case of SLR1 as compared to LR0. Blank entry, blank moves represents the error entries. Okay. Now here, A drives alpha dot, B drives gamma dot. So you have two reduce items. So you have to find follow of left hand side in both the cases and take the intersection. If intersection is not equal to 5, that means there is something common. So reduce conflict will be present. Clear? If it is 5, no reduce conflict. I hope it is clear to all of you. Then it is incorrect. Okay, सौभाग्य, if test में दिया था तो वो incorrect था. Okay, look ahead LR1. Now let's talk about LA-LR1 and CLR1. So first of all, we construct CLR1 diagram. If two states are having same productions but may contain different look aheads, then those two states of CLR1 are combined into a single state in LR1. Right? I will show you how. So here there is one more, there is very important point present here, this one. And if you have appeared for GATE 2022 exam, directly one statement question is based on this RR conflict. If there is no RR conflict in case of CLR1, there may or may not be RR conflict in case of LALR1. But if there is no SR conflict in case of CLR1, there will be no SR conflict in case of LALR1. This is very, very important point. Directly questions can be asked. Sorry. Okay. Now let's talk about conflicts in case of CLR1 and LALR1. So here we have the look aheads. So let's talk about SR conflict. Here you can say A is a look ahead and X or Y is the look ahead here. Clear? Now, how it is SR conflict? So carefully see, whenever there is a shift on a terminal, as you can see, there is a shift on X. Fine. Now you have to see the look aheads here. If you have something common in the look aheads, in that case there will be SR conflict. Clear? Is it clear to all of you? That means if you have X here, that is there is a shift on X, and if it is present if it is present in the look ahead of the reduce item, then it is SR conflict. What about RR conflict? You have two reduce items. In that case, just compare the look aheads of both reduce item. So as you can see, A is common here. So yes, RR conflict will be present. Clear? Any doubt? Anyone? Next point is, every LLR1 grammar is CLR1, but every CLR1 grammar need not be LALR1. That is correct, because LALR1 is subset of CLR1, right? But if CLR1 grammar you have, it may or may not be LALR1. Now, LALR1 parsers are often used in practicing, and that is similar. That is not an important point, but yes, you should know this, that mostly we use LALR1. Why? Because due to less space. In case of LALR1, it consumes less space as compared to CLR1. Clear? So these are the important points. And now if we talk about the parsers comparison, so this is the order of power. Which one is most powerful? CLR1 is most powerful, right? Then you have LLR1, then you have SLR1, and then you have LR0. And if we talk about the number of states in these parsers, so LR0 will have same number of states in SLR1. It will have the same number of states in LLR1. But in case of CLR1, it will be less than equal to. Okay, that means CLR1 may have more number of states as compared to these three. And that is quite obvious because in case of CLR1, merging is possible, and after merging we get LALR1. Clear? Is it clear to all of you? So this is the last slide for this compiler design. So here this diagram is very important. So as you can see here, LR0, if a grammar is LR0, definitely it will be SLR1, definitely it will be LLR1, it will be CLR1, right? But we have some unambiguous grammar which cannot be parsed by even CLR1 parser. Okay, and what about LL1? If a grammar is LL1, definitely it will be CLR1. Why? Because it is subset of CLR1. Is it clear? And if we talk about ambiguous grammars, so we have the operator precedence parser which can parse some of the ambiguous grammars and some of the unambiguous grammars. Clear? So that's why we have shown it like this. Is it clear to all of you? So 2 subjects I have completed. Now from here onwards, Anil Prasad sir will continue and he will take 2 subjects, COA and operating system, and he will cover all the important points and formulas that you need to know for this BARC 2022 exam. So guys, stay tuned. Don't go anywhere because this is going to be really important session. And then after Anil Prasad sir, Satya sir will join and he will cover the rest of the subjects. So thank you all of you. Keep learning and stay tuned. Stay tuned. Okay. Yes. Over to you, Anil sir.
Hello students, that's a wonderful session from Anshul. Thank you Anshul. And from this session, in this session especially, we are going to cover the computer architecture and operating system. This is Anil Prasad Surampudi, and make sure that you are going to have a note of each and every slide and each and every point that I am going to cover in the next 1 hour or so, because I am going to give you some important points in addition to the regular the formulas. In this session, I'm going to give you 2 subjects. That is, the first one is COA and the second one is operating systems. Let us start with the computer architecture and organization. When it comes to the computer architecture and organization, first of all, you need to understand before you appear for every examination, any kind of an examination, that you need to think from the perspective of a designer, right? That is, when we deal with the computer organization and architecture, we are no longer Saubhagya Nayak, yes, good morning. Yeah, we are no longer an end user. We are no longer using the system. We are now the designers of the system. That means we are the designing each and every entity of the computer system. That is including the CPU, including main memory, and including I/O devices. And we are going to design some additional things. That is how to get the computer system performance at the utmost level. So we will start with the CPU design straight away. I'm just going to give you a few points, make a note of it, and if you have any doubts, please share it in the YouTube comment section. So let us start with the CPU design. The CPU design is also called instruction set architecture. When it comes to the topic, it is also called instruction set architecture. In instruction set architecture, we do have primarily 3 design entities. That is, in CPU, we do have ALU, we do have control unit, and we do have a register set. The first one that we need to design is a register set. Second one that we need to design is the ALU. And the third one that we need to design is the control unit. So let us start with the registered set design. If you ask me, sir, what is the purpose of each and every entity here? First of all, let us understand this register set will provide you the storage provision for concurrently executing instruction and the associated data. You know that the programs are residing within the main memory. When the programs gets executed, the instruction within that program will be fetched by the CPU one by one, So CPU will be able to execute the instructions one by one, after which the program will get completely executed. So what is the CPU's job? CPU's job is only to execute the instructions one by one. Okay, so when an instruction is getting executed, this instruction must be brought into the CPU. When instruction has been fetched into the CPU, this instruction must be residing within the CPU for a while. For that, we need to have a register set. So when instruction comes, it also brings some associated data. So CPU needs to store some additional data along with the other instruction, along with the currently executing instruction. So we need to have a register set. Next, ALU design. When it comes to the ALU design, first of all, if we can talk about the purpose of the ALU will take care of execution of each and every instruction. During an instruction execution, each and every instruction is going to perform an operation. This operation could be an arithmetic operation or a logical operation. Except some data transfer instructions, every instruction is going to perform either an arithmetic operation or a logical operation. All these operations will be performed within the ALU. So ALU primarily is going to perform three different kind of an operation. The first one is arithmetic operations, second one is logical, and the third one is shift operations. And now, what is the purpose of the control unit in the system? The control unit purpose is to synchronize all the activities of the system. Control unit is going to master the clock which is connected to the computer system. During every clock pulse, there will have to be a specific transfer or an operation assigned. That is, for example, in T0, let us say in the very first clock pulse, there has to be a transfer from main memory to CPU. Control unit exactly makes sure that this transfer will happen in a hassle-free environment. Every clock pulse is assigned to some specific operation. Control unit makes sure that that specific operation, whatever it is going to be performed within that specific clock pulse. Any doubts so far you can ask me, because we are entering into some important details, that is, we are going to design the register set. Any doubts so far? Am I audible and visible? Yeah, fine. Now, let us start with the register design. First of all, if you talk about a register design, these registers in any CPU can be designed in three ways. If you want to go for a register design, you can adopt one of the following techniques. It could be single accumulator, second one is general register, and the third one is stack organization. If you actually can understand single accumulator organization design, rest of the register designs will be made very simple. Because in the single accumulator organization, we do have some registers which are special purpose registers which are going to serve, which are going to store some specific kind of a data. If you actually can understand this, single accumulator organization registers, you will be able to understand easily both general register organization and stack organization. Okay, so let us get into the details of basic registers and that are available in single accumulator organization. Yeah. Now, these are the registers that are available in single accumulator organization. The first one is a program counter, which is going to hold the address part of the next instruction. If the current instruction is a 23rd instruction, the current instruction is available at 23rd address of the main memory. Next instruction, let us say it is available at 24th address. PC, our program counter, is going to hold the address part of the next instruction, that is 24. So every time PC, program counter, is going to get updated to the address part of the next instruction. Address register. When it comes to the address register, this address register will be used by the CPU to communicate with the main memory. Let us say CPU want to access the main memory. For that, CPU will refer an address. This referred address by the CPU will be transferred to the address register, because the address register can communicate with the main memory through the system address bus. System's address bus is directly connected to the address register, and this is the very reason why address register will be used by the CPU to communicate with the main memory. The moment an address is transferred to the address register, this address will be transferred to the system's address bus, from which the actual address within the main memory gets located, from which we will be able to access the data. CPU will be able to access the data. This is the purpose of the address register. The next one is the instruction register. The instruction register is primarily used by the CPU to store the concurrent instruction that is being executed. current instruction that is being executed by the CPU will get stored in the instruction register. Next one is the data register. What is the data register? In the single accumulator organization, the data register is going to be primarily used to store the current instructions data operand. Here, I'm just going to give you 2 points. In the single accumulator organization, in any organization, let us take, when you want to execute an instruction, that instruction, as I told you, it can perform either an arithmetic operation or a logical operation. For an instance, let us understand that one instruction is executing an arithmetic operation. One instruction is performing an arithmetic operation. So in order to perform an arithmetic operation, how many operands we do require? We do require 2 operands, right? So one operand will be stored eventually and will be brought eventually from the main memory to data register. Mind you, all the operands, all the instructions for every instruction are stored in the main memory. So anyhow, as in order to execute the instruction, we do require 2 operands. One operand will be brought from main memory to the data register. So the data register is essentially going to hold one operand of the concurrently executing instruction. You can ask me, sir, what is the second operand? One operand you already transferred to the data register. Where is the second operand? Second operand in the single accumulator organization will always be implicit, will always be by default the accumulator itself. Second operand is the content of the accumulator. So every time when an instruction is getting executed, one operand will get transferred from main memory to the data register, and the second operand being accumulator all the time. Any doubt so far? You can ask me. The next one is a temporary register. Hold on, listen to me very carefully. In any register, it could be general purpose register, it could be generalist organization, or it could be a single accumulator organization. If there exists a register called temporary register, it could be I3, I4, I5, I9, go to 8086. If you ever come across a name temporary register, what kind of a value that gets stored into the temporary register? Stay focused and write it down somewhere. A temporary register is going to store the temporary values of your program. Let me explain this precisely. You may pass a parameter to a function. This parameter to a function, the scope of this variable is very limited, very confined to a specific module of that function, right? So whenever we need to access those variables and we need to use that variables during the program, those will get transferred to the temporary register. So temporary register is primarily used to store your temporary variables, such as passing the parameters to a function. Understand and write it somewhere. Okay, because in many of the architecture we do see often this temporary register. And next, I do have 2 registers. First one is an input register, and second one is an output register. Any doubt so far? Yeah. When it comes to the input register, these input register and output register, whatever it is, will be a communication medium in between peripheral devices and the main memory. When you give a character by using a CPU or a mouse, this input character, the character that is input by the user, will initially be transferred to the input register. Finally, from the input register to the main memory, there will be subsequent transfer, because whenever we are giving an input, our idea is to transfer this character to the main memory where our data and the programs are residing. So every time when you give you an input, this input will be transferred to the main memory via the input register. Similarly, what is the output register? What is the data that gets stored by the output register? If you take an output from the system, the data that is originated in the main memory will initially be transferred to the output register. From the output register to the peripheral device, it will get transferred. So this input register and output register are essentially going to communicate in the communication medium in between IO devices and the main memory. The next thing is stack. Yeah. What is the purpose of a stack? Why do we need to have a stack in our system? There are several ways that we can, several dimensions that we can have a look at the stack. Being a programmer, you will have a look at the stack from one direction. Now I am going to give you completely the other dimension when we actually design the stack. Mind you, several times I told you that we are the designers of the system right now, including the stack, every entities of the system. are being designed by ourselves. So what is stack for a designer? For a programmer, rather for a designer, a stack is an essential data structure, rather the most important data structure, because the stack is going to hold the return addresses when a function calls another function, when a routine calls another routine. Function A calls function B, routine A calls routine B. So A's return address, where it is going to get stored into the stack. Stack is going to hold return addresses. Every time when a routine calls a subroutine, the current routine's return address must be stored into the stack. In addition to which, stack also holds a local variable. Every time when a local variable is accessed, that local variable will directly get transferred to the stack. In addition to which, some computer system uses, some CPUs uses the stack to also store the flag register. You know the flag register of the system. This flag register can also be called as a PSW word, program status word, right? So this PSW or a flag register will get stored into the stack by only some CPU. This is optional. So when you look at some processors such as Snapdragon or some other process, and if you have a look at and you find out that the flag register is not being stored into the stack, don't ask me. So precisely I'm saying only a few processors implement this technique to store even the flag register values into the stack. This is the major purpose of the stack. Next thing is coming to the addressing mode. When you execute an instruction, this instruction will hold an operand most of the times in the form of an address. Eventually, when you execute an instruction, we need to get the operand. How are we going to get the operand? By using the various addressing mode. Each and every operand can be specified in different addressing mode. These addressing modes will give you a way to find out the location of the actual operand, the actual location of the operand. Once again, let us understand this carefully. I want to execute. What is my job? When I execute an instruction, what should be my job? I need an opcode. Eventually, I require two operands, right? I don't know from which source the operands are being accessed. I don't know where the operands are available. Being a programmer, finally, I should be able to get the operands into the CPU, and I will be so that I will be able to send those operands into the ALU. Finally, the ALU will be able to perform any operation. For that, we need to get the operands, right? Hold on. These addressing modes will give the programmer a provision to access all the features of a program. Why do we require an addressing mode? Understand carefully. In the programmer, there will be a feature of loops. If you want to exploit the feature of the loops, we need to use one of the addressing modes. If you want to exploit the concept of pointers, we need to use another addressing mode. If you want to declare a variable, exploit the concept of variable, you need to use one more addressing mode. So I'm going to give you all these addressing modes and their applications in the program so that you will be able to understand what is the actual link. Mind you, a detailed session will be taken for all these things. Just now I'm going to give you a brief brush up, right after which in a few days time we are going to have a complete detailed session on this. But make a note of it and write down all the things what I'm saying. So let me tell you repeatedly, because this is very important session for your BARC 2022. Okay, so the first addressing mode will be the direct address. In the direct addressing mode, instruction, I will put it this way. In the direct addressing mode, every instruction will have an opcode followed by some address. Okay, let us say the address is 450. Taking this 450, I will directly go to the main memory, and at the 450th location, I will have an operand. Okay, this operand is the actual operand that I'm looking for. Okay, so in the direct addressing mode, instruction will have a direct address in which when you access the main memory, you will get the actual operand. The next one is indirect addressing mode. In the indirect addressing mode, the address that is specified in the instruction will be an indirect address. That is, when you go to that specific address, the value that is available at a specific address is one more address. That is, this 500 will no longer be a value right now. This 500 is one more address. So in 500, you are going to get the actual operand, whatever it is. So in the direct addressing mode, the address will give you the direct address. In the indirect addressing mode, the address will give you the indirect addressing mode. So in the indirect addressing mode, when you access the memory for twice, you will be able to get to that operand. Any doubt so far? Saubhagya? Yeah. Implied addressing mode. When it comes to the implied addressing mode, just a minute. Any doubts? No doubts. Right? When it comes to the implied addressing mode, some instructions doesn't have any operand provided within it. For an example, there is one instruction called INC. So INC stands for increment. What to increment? There won't be any explicit operands provided within the instruction. Instruction itself contains the operand implicitly. That means that when you say when an instruction is said to be in an implied addressing mode, the obvious operand will always be accumulator. What is INC stands for? What does INC stand for? INC exactly stands for incrementing the accumulator. We don't need to put the accumulator operand within the instruction, because the contents of the accumulator will obviously get updated, because accumulator is an implicit operand for every implied instruction. Okay. The next one is immediate addressing mode. In the immediate addressing mode, the instruction will have the direct operand present in it. For an example, let me write it here. Add 450. This 450 is neither a direct address nor an indirect address. Rather, it's a direct operand. This 450 is the direct value which is considered to be an operand. Okay. Next one is a register mode. The instruction is going to hold a register, a processor's register, which is the actual operand. For an instance, add is followed by one register R1. This the value of R1 is the actual operand in this case. So in the register addressing mode, the instruction is going to have one processor's register in which the actual operand is available. Register indirect, which is similar to indirect addressing mode. The register which is specified in the instruction is now holding a memory address. The value of the register is going to hold a memory address. Let us say R1 is equal to 520. This 520 in the register direct is the actual operand. In 520 in the register indirect addressing mode, this 520 will be the indirect address. Rather, is going to give you a memory address. So register indirect mode, the register that is available within the instruction is going to hold a memory address. You can't treat that as a direct operand, taking which you need to go to the main memory in which you're going to find out the operand. The next thing is auto increment or auto decrement addressing mode. Simple. Auto increment, auto decrement addressing modes are pretty much similar to register indirect. Only the exception is the register which is specified in the instruction will be incremented or decremented. Okay. In the auto increment addressing mode, the value that is specified in the the register that is specified in the instruction will get incremented after performing the operation. In the auto decrement addressing mode, the register value that is specified in the instruction is going to decremented before you perform the operation. So auto increment or auto decrement mode is like A++, auto increment, minus A, auto decrement. So this will be used for use. Okay. Relative addressing mode. What is relative addressing mode? In the relative addressing mode, we have a displacement provided within the instruction, which is going to be added to the program counter value in order to get the effective address. That is, I will write here, the current instruction is 23rd instruction and program counter is at 24. The current instruction is, let us say, call 520. So 520 is the offset that is given within the instruction. The offset that is given within the instruction should be added to the program counter value in order to get the effective address. So now in the relative addressing mode, what will be the effective address? 520 plus 24. 544 is the effective address where the branch is going to happen. So in the relative addressing mode, effective address, I will write it here. Effective address is equal to program counter value plus value in instruction. Okay, you can also write as a displacement. Okay, so this is how we're going to calculate the effective address. The next one is base register addressing mode, and the next one is index register addressing mode. In the base register addressing mode, effective address will be calculated as base register value plus value in instruction. Index register addressing mode is very simple. In the place of base register, I'm going to put index register. The contents of the index register will be added to the value that is available in the instruction. Okay, for a simple example, call 520. 520 is the value that is provided within the instruction. The contents of this, the instruction will be added to the base register contents in order to get the effective address. The contents of this instruction will be added to the index register contents in order to get the effective address. So let us understand the purpose of each and every addressing mode here. Direct addressing mode will enable the feature of variable in a program. Indirect addressing mode will enable the feature of pointer in a program. Implied addressing mode is going to update the accumulator for every instruction execution. The contents of the accumulator should always be updated no matter which CPU it is, for which we are going to use the implied addressing mode. Immediate addressing mode is for constants. Register mode is for updating variables. Every time you update a variable, that variable will be transferred to a processor's register. For this, we use register addressing mode, and auto increment, auto decrement addressing modes are for loops, and register indirect addressing mode will serve as a base addressing mode for auto increment and auto decrement addressing mode. Relative addressing mode is for branches. Base register addressing mode is also for branches. Dynamic relocation of the program will be done by base register addressing mode or TC relative addressing mode. Index register addressing mode is for declaring the arrays. Okay, any doubts so far? Fine. Next thing is instruction formats. When it comes to how we design the instruction, we need to understand the instruction formats. When it comes to the instruction formats, I do have two different kinds of instruction format. The first one is locations of the operand. In terms of the location of the operand, we do have a set of instruction formats. We do have other kind of instruction formats also in terms of the number of operands. Now let us understand, when it comes to the location of the operand, how many instruction formats are there. I do have the following instruction format. The first one is the memory reference instructions. Second one is the register reference instruction, and the third one is the IO instruction. That is, every time when you are executing an instruction, we need to get the operands. This operand may be available in main memory. If the operands of an instruction is available in main memory, these are called memory reference instruction. If the operands are available in the register reference, the operands are available for any instruction in the processor's registers, these are called register reference instructions. Rather, if we are directly getting the operand from the IO devices, these are called IO reference instructions. So these are the instruction formats when it comes to in terms of location of the operand. Operands are available in main memory. Those instructions are said to be memory reference instructions. Operands are available in the processor's register itself. Those instructions are called register reference instructions. Operands are available in IO devices. Those operands are directly collected from the IO devices. Those instructions are said to be in IO reference instructions. Next, instruction formats based on number of operands. In terms of number of operands, I do have four types of instruction formats here: 3 address instruction, 2 address instruction, 1 address instruction, and 0 address instruction. 3 address instruction will be like add A comma B comma C. Conventionally, A is equal to B plus C. The first one is the destination, rest of the two are the sources. In the 2 address instruction, right after the opcode, we just have only 2 addresses. Let us say add A comma B, in which the first one is the source as well as the destination, and the next one is only the source. In the two address instruction, the meaning of add a comma b is a is equal to a plus b. In one address instruction, we do have only one address, rather one operand specified within the instruction. Second operand will always be the accumulator. The meaning of this instruction is accumulator is equal to accumulator plus a. Zero address instructions are the stack instruction, and we don't specify any values in the instruction itself. When we say add, without having any operands here, the topmost two contents of the stack will be added. This is what zero address instruction. The control unit design, when it comes to the control unit, as I already told you, the control unit is essentially used for synchronization purpose of the computer system. I do have two kinds of a control unit. First one is a hardwired control unit. Control unit is needed to send the control signals to each and every entities of the CPU as well as the main memory. If the control unit designed by some hardwired logic, that is control unit is designed by, let us say, encoders, decoders, flip-flops and gates, combinational logic circuits, then that control unit is said to be in hardwired control unit design. The control signals are generated by combinational logic gates in the hardwired control unit. And this hardwired control unit is quite faster than microprogrammed control unit, but the problem, the shortcoming of the hardwired control unit is it cannot be updated at all. So most of the computer systems will use microprogrammed control unit, in which all the control signals are available in a binary format. That is, we need to program each and every micro operation, and we need to store it in a ROM, which is going to send a control signal. So obviously all the control signals are available in a ROM in the binary format, because we are programming this directly. So there are two things. One is vertical microprogramming and second one is horizontal microprogramming. The next thing is ALU design. First of all, in order to understand ALU design, in the ALU also we need to design several entities. What must be designed? The first one is I need to design arithmetic unit. My arithmetic unit should be able to perform 4 different tasks. What are those? Addition, subtraction, no multiplication, no division, incrementing and decrementing. ALU will be able to perform these 4 operations. Either you call it as a multiplication or a division will be the derived operation from addition and subtraction. So arithmetic unit will be designed by implementing 4 different operations with 4 operations: addition, subtraction, incrementing and decrementing. 2 additional sub operations: addition with carry, subtraction with borrow. So I need to design an arithmetic unit. I need to design a logical unit. There are 16 logical operations altogether. If we club them and we multiplex them, we are going to get a logical unit. And my ALU should also perform a shift operation, right shift and left shift. Multiplexing unit of arithmetic unit, logical unit and shift unit is going to give my ALU. If you want to design the ALU, you need to design 3 different entities. First one is arithmetic unit, logical unit and shift unit. All must be multiplexed together in order to design the ALU. Now let us talk about the main memory. In the main memory, thank you, Adu. Yeah, good. Now let us concentrate on memory. Main memory, stay focused and listen to me this thing. When you talk about the main memory, most of the questions are originated in cache. First of all, but you need to understand what is cache. You might have several perceptions and several imaginations about a cache. Let me avoid and let me clear all those imagination. The purpose of having a cache memory initially in the system is just, first of all, let me this RAM and ROM I'll talk about later. First, initially, let me talk about the cache memory. Cache memory, the purpose of the cache memory is just only to compensate the speed differences in between CPU and the main memory. CPU is faster, main memory is slow. CPU can execute 1 lakh instructions at a time, but main memory cannot supply the CPU 1 lakh instructions at a time. So total speed of the CPU just gets limited by the main memory speed. This is the very reason why we are going to use a cache memory which is going to compensate the speed differences in between CPU and the main memory, so that the system will be faster, because the cache memory is taking one important responsibility of at par the CPU as well as the main memory. So in the main memory, the design entities of RAM and ROM. I don't need to talk much about RAM and ROM. Let us talk about a cache memory. In the cache memory, we need to talk about a locality of reference. What kind of a data that is going to get stored in the cache memory, which will be defined by locality of reference. There are, again, when it comes to the locality of reference, two locality of references. One is temporal locality and one more is spatial locality. What is temporal locality? If an element is accessed right now, that element can get accessed in the near future. So please transfer that element also to the cache memory. If you directly access any element from the main memory, that element may be accessed in the near future. So the currently accessed data element must be transferred from main memory to the cache memory for the future references, which is called temporal locality. What is spatial locality? Spatial locality is if an element is transferred, if an element is used by the CPU right now, in addition to the currently accessed element, the elements that are maintaining the closer proximity can also be accessed in the near future. Let us say I access an element which is available at the 23rd address of the main memory. Temporal locality states that transfer the 23rd element to the cache memory. Spatial locality says that not only 23, please send all those elements which are closer to 23. So I need to send 21, 22, 19, 18 in addition to 24, 25. So total block of elements will get transferred to the cache memory. The next thing is, when it comes to here, we are going to understand some important things. That is, we can have any levels of the cache. So, but basically we use, two levels of the cache in some computers, most of the computer system. In a single level cache, we can have a single level cache, we can have a two level cache. The average memory access time formula, as you know, it is H1 T1, 1 minus H1 into T1 plus T2. What is H1? H1 is hit rate of cache. T1 is access time of cache. Access time or access latency of cache. Yeah, sure. We're going to Kaushal Agarwal. We are going to have a detailed session. It's just a formula, revision session. So we'll have a complete detailed session in which I'm going to give you all the questions in the world. You don't need to worry. So, for this, session, just do not prolong it too long, because it's just the purpose of this. The objective of this session is just to go through some important points and the formulas. We'll have a detailed session. Okay, mind you, T1 is the access time or access latency of cache. Okay, 1 minus H1 T1 plus 1 minus H1. When you go to main memory during a miss in cache, what is miss? Miss is 1 minus H1, in which we need to add the time which is wasted at the cache T1 to T2, which is the access time of the main memory. T2 is access time of main memory. So in the two level cache, it will be like here, that is H1 T1. First we need to go to the first level cache, in which H1 T1. H1 is the hit rate of the first level cache. T1 is T1 is the access time of the first level cache. In the first level cache, if you don't find it, you will go to the second level cache, in which you need to multiply the miss rate with H2, that is the hit rate of the second level cache, and the time which is wasted at the first level cache will be added to the time which is going to which we are going to spend in the second level cache for accessing the data. So let us say in the first level cache, second level cache, we did not get the data. So first level cache through a miss, second level cache also through a miss. So where we are going? We are going to main memory, in which miss rate of the first level cache, miss rate of the second level cache. This is not plus, it is okay. Miss rate of the second level cache, and the time which is wasted at the first level cache, the time which is wasted at the second level cache will be added to the time which is going to be consumed by the main memory to give you that specific word. This is what average memory access time for two level cache. H1 T1 plus 1 minus H1 into H2 into T1 plus T2, 1 minus H1 1 minus H2 into T1 plus T2 plus T3. Cache memory mapping techniques. Why do we require mapping techniques? Because cache is smaller and main memory is bigger. Let us say main memory address length is 15 digits. Cache memory address length is 19 digits. CPU references 15 digit address. Now taking this 15-digit address, where you are going initially? You are going to initially cache memory. But here there is a mismatch. Cache memory will tell you, I don't have a 15-digit address format. You don't talk to me 15-digit address format. You just talk to me with my 9-digit address format, because my address length is 9. If you talk to me with the 15 digits, how can I give you? So we need to convert this 15-digit address to 9-digit available address in the cache memory. So we do have several mapping techniques which maps a 15-digit address of the main memory to 9-digit address of the cache memory in our example. Okay, because when CPU always refers main memory address length, cache memory has limited address length. So in order to translate that main memory address length to the cache memory address length, in order to find out to which location exactly the main memory address gets mapped, we do need mapping techniques. First one is direct mapping, second one is set associative mapping, and the third one is associative mapping. There is no relation between set associative mapping and associative mapping. These two are two disjointed techniques. These two are relative techniques. Direct mapping has a shortcoming. That is the reason why we went for set associative mapping. Let me show you this. Okay, main memory is 15 digits. Cache memory is 9 digits. 512 words, 9 digits. So let us say CPU sending an address 15 digits. So how 15 digits can be located in the cache memory? Go through the direct mapping technique. In the direct mapping technique, total address reference will be divided into common portion, least significant 9 digits, which is common for both cache memory and main memory, and the remaining portion, this common portion is index and the remaining portion is tag. This index will be located, tag will be compared. Right after you locate the index, if the tag gets compared, that's a hit. If the tag doesn't get compared, that is a miss. Once again, total in the direct mapping technique, total address reference will be divided into two fields. One is the index field, which is the common address bits in between main memory and the cache memory, and tag bits. These are the additional digits. First index will get compared. This index will get located, right after you locate the index, you need to compare the tag. If the tag is compared with the available tag, then that's a hit, otherwise it's a miss. In the set associative mapping, simple, every index in the every address, every location of the cache memory has two tags and two words. So initially what you need to do is you need to divide this index and tag. First you compare the index, right after which you can compare the tag. If the tag is not compared, this is not already a miss. You have another choice of this tag 2. You have another chance. So here set associative mapping will increase the hit rate or a hit ratio. So important notes that are need to understand: address bits will be divided into index and tag field, and again index field get divided into LSB in the line and block fields. In two-way set associative mapping, index is equal to index minus 1, tag is equal to tag plus 1. Let us explain with an example. Let us say address is 32, cache is 15. Initially, what will be the division? Total 32 will be divided into 15 index bits and 17 tag bits. After which this index will be further subdivided into word field and block field. Let us take it index here. I'm writing index here. Total 15 digits and the block size. If the block size is equal to 64 words, least significant bits of the index will be given for the block. Since 2 power 6 is equal to 64, least significant 6 will be the word within the block, and the most significant 9 digits here, because 15 minus 6 is equal to 9. 9 digits will give you the block number. So in two-way set associative mapping, index is equal to index minus 1, tag is equal to tag plus 1. So in the two-way set associative mapping, 15 will become 14 and tag will become 17 plus 1, 18. In the four-way set associative mapping, index is equal to index minus 2, tag is equal to tag plus 2. Mapping rule from main memory to the block to cache is simple. If at all you want to understand a block of the main memory gets mapped to which block of the cache memory, you can implement this rule, that is K mod C, where K is the reference block number and C is the total number of blocks in cache. For an instance, CPU is accessing 12th block of the main memory. and the total blocks in the cache memory is 4. Cache memory blocks are equal to 4. Now, the 12th block of the main memory will get mapped to cache memory to the 0th block, because 12 mod 4 is equal to 0. So, 12th block will get mapped to 0th block. So, address mapping, in the associative mapping, in the associative mapping, any block of the main memory gets transferred to any block of the cache. In the associative mapping technique, we don't have the problems such as direct mapping or set associative mapping. Any block of the main memory can be transferred to any block of the cache memory. There is no mapping rule at all. The mapping rule doesn't fit it. Doesn't get to associative mapping. Associative mapping doesn't require any mapping rules. This is the thing. Now let us get into the pipelining. What is pipelining? In the pipelining, CPU will be segmented. Our ALU will be segmented. Now, why? Because we need to increase the performance. We need to increase the speed up. Okay. So for that, anything else? Any questions so far? Fine. In the pipelining, let us understand a few things very clearly. In a non-pipeline system, the time will be NTN. Let us say there are n tasks, there are n instructions must be executed. Each instruction will take 4 clock cycles. Let us say this is the CPU. This CPU for each instruction will take 4 clock cycles. So in a non-pipeline system, the time will be equal to n. N is the number of tasks. Tn is time required for a single task. So if there are 100 tasks in a non-pipeline system, we require 400 clock cycles. In a pipeline system, it will be k plus n minus 1 into tp, where k is the number of segments. I will write it. K is number of segments, n is number of tasks, tp is segment time. Speed up is non-pipeline system by pipeline system time, which is NTN divided by k plus n minus 1 into tp. If you exactly translate, you will be just left with k. For this, we're going to have a complete session. How speed up will be reaching to k, I will explain you in the next session, in the detailed session. Hazards in the pipeline. Pipelining meaning, every time we look at the pipeline, we may feel that the speed up can be always equal to k. No, that is not possible, because there will be several difficulties in the pipeline. First one is structural hazards. Structural hazards happens when 2 segments of the pipeline, when 2 segments, requires the data from the same resource. Let us say I have a printer and I have 4 segments in the pipeline. First segment, second segment, third segment, and the fourth segment. This is only simple example, superficial example. This printer is being accessed by segment 1 and segment 3. But printer is only a single resource. If it is a single resource, it can either serve segment 1 or segment 3, but not both. So we are in a situation called as structural hazards. We need to avoid a hazard unless hazards lead to stalls. Stalls will affect the pipeline time. Next one is the data hazards. 2 subsequent instructions, 2 consecutive instructions are dependent on each other. I will give you x is equal to a plus b, y is equal to x plus z. Right? X is equal to a plus b. Here x is the result. In the next one, x is one of the source, one of the operand. Unless this instruction gets executed, this instruction cannot be fetched at all. So this is, we see that there is a data hazard. It is a data dependency. Third one is a control hazard. Let us say 2 instructions x and y. Okay, x is a call instruction, conditional call instruction, conditional branch instruction. If the conditional branch instruction, unless the condition gets evaluated, we don't know what is the next instruction. So control hazards, all these hazards are going to impose some stall cycles. We need to work on how to avoid the stall cycles. Now pipeline time with the hazards is calculated as, how to calculate a stall cycle. Stall cycles will be equal to k minus 1. If the number of segments are equal to k, and the stall cycles will be equal to k minus 1. Here, there are several exceptions. I'm going to explain all those exceptions in the detailed session. F is equal to 1 by t and t is equal to 1 by f. Frequency is equal to 1 by time and time is equal to 1 by frequency. Pipeline time with the stalls is 1 plus rate of the instruction incur the stalls into stall cycle. Please write it down, which is very important. TP, what is TP? TP is one segment time. Here, TP can be defined as a max stage delay, max buffer delay. Let us say different segments take different clock cycles. This is taking 2, 3, 4, 2. Here, what is the maximum segment delay? Maximum segment delay is 4. Okay, every segment will have an intermediate buffer. These buffers also will have some delays. So TP is a mixture of max stage delay plus max buffer delay. Again, this is all about pipelining. Now we are done with the COA, and anyhow we're going to have a detailed session. I'm going to give you every possible detail of the COA in one of the upcoming sessions. Now let us get into the operating systems. In the operating system, let us understand for process creation. When it comes to the process creation, we do have several rules that are needed to understand. What is the process creation? Parent process need to create a child process. Let us say this parent process will have to create new process. I mean, if you take the example of Linux, parent process will execute one system call which is called fork. Okay, and when the fork system call gets executed, a new child process will get created. Here, I need to explain you a few points right after this slide. Please remind me. Child process. Right after the child process has been created, child process will typically execute a system call called which is EXEC. Write it down carefully. We are going to have a complete bang of session of this. Okay, what is EXEC system call? When an EXEC system call gets executed, the child process will be given the parent's memory space. I'm a parent. I have a memory location from 200 to 300 are allotted to me. If I create a child, I need to show a hideout for my child. What is the hideout of the child? The child's hideout is my hideout, my parent's address space. So, in order to use its parent's address space, child process will execute EXEC system call in Linux. So, when EXEC system call gets executed, operating system will allow the child process to occupy its parent's address space. Next thing is parent process. The moment the parent successfully creates a child process, parent process most of the times will wait till child process finishes. Okay, for that, parent process will issue a wait system call. What is this wait system call? Wait system call restrict the parent process to be in the ready queue again. So why it has to get restricted? When it comes to the ready queue, operating system will schedule it to the CPU. As long as the child is executing for a parent, there is no purpose to execute in the CPU because there is nothing to do. Okay, so for that reason, parent process will wait till the child process finishes by executing a system call. This wait system call requests the operating system to put the parent process in a waiting state. Okay, when parent process will be able to resume the moment child process terminates and executed, the parent process will be able to come back into the ready queue. So the child process completely right after its execution, it is going to issue an exit system call. Right after this exit system call, the parent process will resume. So these are the things that are needed to be completely understood during the process creation. Okay, here let me tell you, fork has three outcomes. Fork can have an outcome 0, fork can have outcome 1, fork can have an outcome which is -1. So what are the differences? When the fork returns 0, for these two cases, child process creation is successful. But if the fork returns -1, child process creation is not successful at all. So again, you can ask me, sir, fork has two instances in which you say that child creation is successful. What is the difference of each and every instance? Let me tell you. If the fork returns 0, fine, child process is created and child is executing in the CPU. If the fork returns 1, child process created but parent is executing. Okay, so this is the difference between the difference between 0 and 1 when a fork gets executed. Then the next thing is process synchronization. Understand several things in the understand several things in the process synchronization, which is very important. Process synchronization, in order to protect the critical section, we may use several we have a lot of solutions, but directly we talk about the Peterson solution. Why we talk about the Peterson solution all the time? Peterson solution gives us a good algorithmic approach which satisfies all the criteria. such as bounded waiting, progress, and mutual exclusion. But Peterson's solution cannot be implemented. But why we are going to have a research on the Peterson's solution? Because it will tell you how a simplest code can satisfy all the criteria of critical section. Peterson's solution is only for research purpose. It cannot be implemented to protect your critical section. Tomorrow, when you develop an application, you can't use the Peterson solution because it doesn't have any atomic, instructions. So Peterson's solution is not a proper solution, is not a right solution to protect your critical section. And now you can go to hardware instructions such as test and set lock or a compare and swap. But hardware instruction provides atomicity. Hardware instructions are atomic. Only one process will be able to access this hardware instruction, hardware lock. But here the problem is hardware instruction doesn't satisfy bounded waiting. Bounded waiting must be attributed to hardware instruction by the programmer itself. So the programmer need to take additional care to attribute this bounded waiting to hardware instructions such as TSL. How we are going to have in the detailed session. Semaphores are the robust solutions. Either you take a hardware solution or a software solution. We are going to face some problems which is called a busy waiting. What is busy waiting? Let me tell you. What is the busy waiting? When a process acquired a lock, one more process searches for a lock and the lock is not available. What that process will do? The process will be in the waiting state. What is this exactly? I will explain you. I am the process. I got the lock. You are the other process which are waiting for the lock. So when you check for a process, when you check for the lock and it is not available, you will be in a loop, right? Look at all the solutions. Look at all those locks. All those locks are involved in having a while loop or a loop or some loop. Okay, when you are in a loop, you will be in the infinite loop when the lock is not available. So every time when you get into the CPU, you are going to waste the time simply in executing that instruction within the loop without doing any productive work. So this is called busy waiting. That kills important clock cycles of the CPU. When you get into the CPU, you must be able to do some productive work, not simply executing one simple and useless instruction. So what we need to do is we just need to avoid this busy waiting. So what we'll do is we'll implement a semaphores in which busy waiting can be somewhat avoided. Let me tell you, even semaphores, busy waiting problem cannot be completely avoided at all. Semaphores also has busy waiting. How? We'll see later. Semaphores will have busy waiting, but these semaphores are the robust solutions than the other one. Okay, semaphores can be made atomic by protecting wait and mutex locks. That is, in the semaphores, you need to perform two operations. Okay, wait operation and a signal operation. These semaphores, what we need to do is this wait must be protected by using the locks. Okay, so that only one process will be able to access the semaphores at a time, because semaphores is any variable, integer variable. If it is an integer variable, there is always a prone to be accessed by multiple processes. So we need to protect this wait and signal by using mutex locks or some other locks that are available. This is important. Wrong usage of the semaphores will either lead to a deadlock or more processes can be in the critical section. Next thing is process scheduling. Important terms are response time must be less than once again. When it comes to the response time should always be less than once again. If the response time is more, the user will lose the interest. You opened a VLC media player. The VLC media player should be opened within 1 second, which is the response time for the program that is given to VLC media player. That is the time that is given to VLC media player program. So every time when you open some file or a program, you just require, being a user, you require a minimal response time. Okay, so the response time should always be less than 1 second. Okay, what is the turnaround time? Simple. Departure time minus arrival time. The moment the process created will be available in the main memory, right after which, after some time, it will be sent to the CPU. In CPU, it will spend some time, after which it will go into completely get executed and leave the system. So, leaving the system and arriving the system. The difference is the turnaround time. Waiting time. Waiting time is, waiting time is turnaround time minus execution time. Waiting time is total turnaround time minus execution time will give you how much time it has been spent in some waiting queues. Okay, interrupt latency. When it comes to RTOS, real-time operating system, Real-time operating system scheduling criteria is different. So here we need to minimize the interrupt latency and dispatch latency, and they need to meet a strict requirement. If the interrupt latency and dispatch latency are more, we won't be able to process a critical processor, a real-time process. So this interrupt latency and dispatch latency must be made very minimal indeed. Deadlocks. So here simple, how to avoid a deadlock? In order to avoid a deadlock, how many resources that we need to have for a system? We need to have we need to find out how many resources that are needed for a system. The number of resources that are needed for the system can be calculated very simply as follows. That is, if more processes are required, requesting for more resources, the system should have sufficient resources to satisfy at least one process max request, and the remaining process max minus one request. Okay, this is the condition to completely avoid a deadlock. Number of resources, rather, when it comes to the number of resources, the system should have sufficient resources to give all the process that are required by at least one process, and the remaining process should be satisfied the resource requirement minus one resources. Okay, this is how we avoid deadlock. So mutual exclusion can't be avoided under any circumstances, because under any circumstances mutual exclusion cannot be avoided at all. So in order to avoid it, see, there are four conditions: mutual exclusion and mutual exclusion. Tell me what are the necessary conditions for deadlock? Mutex, circular weight, and there are two other. Fine, anyhow, in which mutual exclusion can never be avoided at all. Okay, because mutual exclusion, if the mutual exclusion is avoided, several processes can use the same resource. So under the four necessary conditions, mutual exclusion can never be avoided at all. How? We are going to look at in a detailed session. Just a minute. A single instance of each resource type under cycle in RAG resource allocation graph will show the presence of a deadlock. There is a resource allocation graph and only a single instance, and there is a cycle. We are in a worse situation called deadlock. Okay. Now let us go to the virtual memory. In the virtual memory, there are several points to discuss. The first one is the page table size, in which how page table size is going to get calculated. Page table size is just nothing but number of pages into size of each entry in terms of bytes. Each entry will have a frame number. How many digits are required by the frame number? How many bytes that are required by the frame number, including additional digits such as valid digit. Okay, so the page table size can be calculated as number of pages into size of each entry in bytes, including additional digits. These additional digits like valid digits are actually are important to be present at every location of the page table, every entry of the page table. So virtual address has two entities, such as page number and page offset. Page offset, page virtual address. Yes, when it comes to the virtual address, let us say there is a 15-bit virtual address in which least significant bits will give you page offset, most significant bit will give you page number. Physical address has two entities, block number and word address. About this physical address, we already discussed in the memory. Okay, so this is it from my side. I hope you have written all the things what I stated right now. And now I'm going to hand this session over to Satya sir, and he's going to take many more topics. Thank you. That's it from my side. Over to you, Satya sir.
Hi, hello, good afternoon, everyone. Welcome to the most comprehensive preparation app for all exams, BYJU'S Exam Prep. Now, I'll continue the formula revision for some more subjects in the computer science. I hope you are enjoying the session. Already Anshul sir and Anil sir has revised some subjects important points. So guys, Please mark your presence. Those whoever have attended the session, whoever were watching the session, please do mark your presence. Hello everybody again. Am I clearly visible and audible? Could you please confirm? Everyone, whoever are watching, please confirm, am I visible and audible? Saubhagya Nayak, Hopper, Kaushal Agarwal, Pinky Das, Abhishek Pant, Gautam Shivam, Vaibhav Kansal, and everybody. Am I visible and audible to you all? Great. So before I start, let me introduce quickly myself, Satyanarayana Kaitepalli. I'm a research scholar with 14 plus years of teaching experience, and I have mentored more than 30,000 students all over India in the GATE and PSU segment. I am qualified in GATE, SET, and also certified by Cisco into networking and programming. Before I start, this is a gentle reminder for GATE 2023 aspirants about the strategy, how you have to approach for this GATE 2023 preparation by Mr. Rakesh Talreja sir on 19th Feb, that is tomorrow at 8 p.m. So do join, try to inform your juniors or your friends, whoever are appearing for 2023 GATE exam about this strategy workshop, and also please inform the students whoever are writing this ESE exam that there will be analysis of the same ESE 2022 prelims on the same day, that is 20th Feb at 6 p.m. for non-technical paper 1, and at 8:30 p.m. for paper 2. Okay, now what subjects I will be doing the revision? First, programming data structures, algorithms, computer networks. So majorly I will be revising the important points and formulae of this computer networks, PDS, algo. Okay. So firstly, let us discuss computer networks. Guys, for any exam you prepare from the subject computer networks, firstly, definitely you have to go through the OSI model, the Open Systems Interconnection Model, which is developed by ISO. So according to OSI, we know there are 7 layers, starting with the layer 1, physical layer 2, application layer, that is layer 7. Right? In these, application, presentation, and session layers are software layers, means we can see the existence of these layers in the form of software, and network, data link, physical, we can see in the form of hardware, whereas the transport layer is called intermediate layer. Right? So beside every layer, the major functionality of that layer is mentioned. Application layer is basically providing the interface to the user to provide his message, and presentation layer is responsible for translation, encryption and decryption, and to compress. Session layer is for establishing the session and managing the session, terminating the session. Also, it is responsible for this socket allotment and to load this required API and all. And transport layer, this is majorly responsible for the reliability and error free delivery of the messages, means here to handle with errors. Network layer is responsible basically for source to destination delivery, routing, IP addressing. Data link layer is responsible for framing, hop-to-hop delivery, error control, flow control, MAC addressing or physical addressing kind of functionalities. Physical layer, which establish the physical connection between the nodes. So it has to take care of all the specifications that are needed by the transmission medium, and it is responsible for encoding, decoding also, right? So here you have got the major functionalities of these 7 layers along with the layer names. Okay, so you have to revise this OSI model and functionalities without fail, because there could be a question asking the so and so functionality is the responsibility of dash layer, like encryption is performed by dash layer, or token management is the functionality of dash layer, or we can say flow control is the functionality of dash layer. In that way we can expect a question in the BARC. So please go through the functionalities of each layer once before you go for the exam. And for every layer we have got a terminology for the data. At application, presentation and session layers, we can simply call the data as simply PDU, like application protocol data unit, presentation protocol data unit, session protocol data unit. But when it comes to transport layer, the packet arrived at transport layer is termed as segment, and at network layer the same we call as packet. At a data link layer we call it as frame, and at physical layer we call it as bit. Because in one of the gate exams, I think in 2012 or so, we have got a simple direct question in the gate. The application layer PDU is called as dash. Options were message, segment, packet, frame. So what it is? Message. So in the same way, you can also expect a question in the BARC exam asking for the terminology of the data at respective layer. Okay, and followed by OSI, definitely you are supposed to go through the TCP/IP protocol suite once. We know application layers, OSI models, application, presentation and session layers are merged into only one layer. We call it as application layer in TCP/IP. Transport layer is preserved. Network layer is also preserved, but we can call it as internet layer in the TCP/IP model. Data link and physical layers are also preserved. So in TCP/IP total we have 5 layers, whereas in OSI we have 7 layers. At which layer what protocol operates is clearly mentioned here. This is also important, because by giving, like I can say RIP is the protocol operated at dash layer, or I can say UDP is the dash layers protocol. In this way you can get a question in the BARC. So definitely please go through this protocol suite and the respective layers like telnet, FTP, SMTP, DNS, RIP, SNMP, HTTP, HTTPS. All these are operated at application layer. TCP, UDP are transport layers protocols. IP, IPv4, IPv6, both versions will come. ICMP, IGMP, these will come at network layer and the routing protocols also. And ARP, RARP actually serve both network and data link layers, we can say. Address resolution protocol and reverse address resolution protocol or inverse address resolution protocol. And Ethernet, token ring, frame relay, ATM kind of standards or protocols operates at physical and data link layers both. So I request all the BARC aspirants to go through these protocols and layers before you go for the exam. Okay, guys. However, all the session PDF will be available to you on the Telegram channel. So if you have not joined the Telegram group yet, please do join my Telegram group so that you will get the PDF of the same. Okay. And then in the computer networks, definitely this is required to know, to revise. What are different types of delays if you are sending a data from sender to receiver? There can be several intermediate stations in between. If so, to send a packet from sender to receiver, what is the total time needed? Total delay. That is classified into 4 different forms. What they are? Transmission delay, propagation delay, queuing delay, processing delay. What is transmission delay? It is the time to load the packet into the channel. That is transmission delay. And the journey time from one node to the other is called propagation delay. We know a message consists of multiple packets. So when one packet is under loading, what about the other packets? They are waiting to be loaded in the queue. So the time spent by the data packet waiting in the queue before it is taken for execution, that is what you say, queuing delay. The same way, what is processing delay? It is the time spent by the packet at the node. At the node, whatever the time taken by the packet, that is called processing delay. In these 4 different delays, generally queuing delay and processing delay are minimum or negligible. If given, we will definitely add, otherwise we can say they are neglected. So leaving these two, what is the total time we can say? It is the summation of transmission delay and propagation delay. So what is transmission delay? How we calculate transmission delay? That is the packet size or length of the packet divided by bandwidth of the network. This is the formula for transmission delay. And for propagation delay, length of the channel or distance between the nodes. Here need not to be sender and receiver. Here you can say between one node and another node. Whatever is the propagation distance divided by transmission rate. While you are using this formula, please be cautious. Be careful about the unit conversions. Okay, in terms of meters, kilometers, bits, bytes, kilobits per second, megabits per second. So please be careful about unit conversions. Okay, and then please go through these IEEE standards once in the computer networks before you go for the BARC exam, because there is a possibility of asking a question. IEEE 802.4 standard is technically termed as token bus. 802.5 token ring. 802.3 Ethernet. At least till 802.5 and 802.11 and 15. I'll just keep a tick on it. At least you please try to remember the names of these 7 standards. Or even you can say this 802.6 also. Okay. 802.11 is what? We say wireless LAN. Wireless LAN. And 802.15 is wireless PAN. Bluetooth comes under this. 802.15. Wi-Fi comes under this. 802.11. Okay. And in Ethernet, again, there are substandards. Those substandards I have given in the below table as fast Ethernet, gigabit Ethernet, 10 gigabit Ethernet, and their speed also mentioned. So please go through these standards, everybody, once at least before you go for the exam, right? Then please refer this frame format of Ethernet once, because it is very expected. The minimum length of the frame is what? 64 bytes, and the maximum length is 1518 bytes. This is minimum, whereas this is maximum. And from where the frame starts from destination address. From here the frame starts, not from the preamble. Not from the preamble. From the destination address, the frame is considered to be till CRC. So this is what we say frame. So the length, minimum length of this frame should be 64 bytes. In this 64 bytes, 18 bytes is the header. 18 bytes is the header. So when 18 bytes is the header, what should be the payload? Data is here what we say payload. Minimum payload should be 46 bytes. Max payload can be 1500 bytes to match the 64, 15, 18 constraint. So on this, around this, you can expect a question. So please revise this frame format everybody once. And then definitely it is required, very important, mandatory to revise the sliding window protocols. Very important topic. What are different sliding window protocols? Of course, we have two classifications for noiseless channels, for noisy channels, but I am just presenting the important, the popular three protocols only here. They are stop and wait ARQ, go back, and selective repeat. And how do you calculate the efficiency? This is very important, guys. That is simply I can say efficiency mu is equal to window size divided by 1 plus 2a. What is the window size for the here? Whose window size? Sender's window size. So what is the sender window size in stop and wait ARQ? 1. Receiver window size is also 1. When it comes to go back n, what is sender window size? N, capital N. What is capital N? This is 2 raised to n minus 1 for go back n. And for selective repeat, what is sender's window size? 2 raised to n minus 1. In one of the gate exams, this is asked. For selective repeat protocol, what is the sender's window size? Sender's window size, receiver's window size is same in selective repeat. That is capital N. That is 2 raised to small n minus 1. What is that small n? Minimum number of bits required for sequencing. Small n is number of bits required for sequencing the frames. So if you have total 16 frames, 4 bits are required. If you have 32 frames, 5 bits are required. Even if you have 20 frames also, minimum 5 bits are required. So that you have to take a cap. Okay. So minimum number of sequence numbers required. Total how many sequence numbers are required for stop and wait? 2. For go back n, capital N plus 1. That means 2 power n. Sorry, this is a small n. 2 power n minus 1 plus 1 means 2 power n. And for selective repeat, 2 power n. Because 2 raised to n minus 1 into 2. That becomes 2 raised to n only. Right? And retransmissions required if a packet is lost. How many retransmissions are required? Only the last packet is transmitted in stop and wait ARQ. In go back n, complete window frames are retransmitted, and in selective repeat, only the last packet is retransmitted. And bandwidth requirement, as stop and wait send only one packet at a time, bandwidth requirement is low, and in go back and it is high because a window has to be retransmitted, and in selective repeat it is moderate. So CPU usage, if you see, it is low in stop and wait, moderate in go back and high in selective repeat. Why high in selective repeat? Due to searching and sorting required, because you have to sequence the frames at the receiver side and sender side, that's why. And acknowledgements, independent acknowledgement for every frame in the stop and wait, cumulative acknowledgement in the go back and independent acknowledgement for selective repeat. And the type of transmission, you can say half duplex supported by stop and wait, full duplex and full duplex by go back and selective repeat. So I have consolidated the sliding window protocols information here. Majorly efficiency is what you have to take. And by the way, here what is this A? A is equal to propagation delay divided by transmission delay. Okay, right. Then it is required to revise bit stuffing concept once in computer networks. So what is bit stuffing? It is the mechanism of inserting one or more non-information bits, parity bits you can say, into a message to be transmitted to break up the message sequence or for synchronization purpose. So if you take the data link layer mostly followed bit stuffing procedure, there is a predefined delimiter sequence that is called flag, which is what is a flag? 0 with 5 ones, sorry 6 ones, then 0. So this 8-bit pattern is called flag. So in the message, if there are 5 consecutive ones after 0, then what you do? An extra 0 is stuffed. For example, let us say the message to be transmitted is something like this: 110111111001111111110. Suppose this is the message to be transmitted. So after bit stuffing, what is the message that you transfer or transmit? Here if you see, what is flag here? 0 5 ones, sorry 0 6 ones. So what bit stuffing says, do not entertain those 6 number of ones in the message. So if you have 0 5 ones sequence, here you insert extra 0, and again where do you get such sequence? So here you insert extra 0. So after bit stuffing, the message becomes like this: 0, this is the stuffed bit, 0 110011111110, that is the stuffed bit, followed by 11110. So around this a question can be prepared. So please revise your bit stuffing concept once. Okay, then definitely you cannot skip IPv4 header format. So here if you see, the first 4 bits indicates version. So what would be the version? 01004 IPv4, and the next 4 bits indicates header length in terms of 4, like this is actually HLEN, 4 bits only. So suppose I am having this as my HLEN value. What this means? 8. So does it mean 8 bytes is the header length? No. So when HLEN value is 8, you have to multiply that with 4. So if it is 8, that indicates header length is 32 bytes, like this. So the HLEN range is 5 to 15. Why? Because the minimum header length in IPv4 is 20 bytes, maximum header length is 60 bytes. So we have 40 bytes option in the IPv4 header format. Other is fixed header, so which is of 20 bytes. Okay, from here to here we have 20 bytes fixed header. Then we have 40 bytes optional. So every header optional field length will be of minimum 4 bytes or more than that, like multiples of 4 bytes. So you can't have 23 bytes of header, 31 bytes of header, 47 bytes of header, something like that. Definitely the header length would be multiples of 4 only. Okay. Then please revise IPv4 addresses, their range and their subnet mask once. So the IPv4 addresses are classified into 5 groups as class A, B, C, D and E. In this, class D addresses are called multicast addresses. Class E is left for research purpose or experimental addresses, you can say. So what is the first octet range for class A? 0 to 127. The second octet range is 128 to 191. Third octet range 192 to 223. Class D, so not second, third. Class A 0 to 127. Class B 128 to 191. Class C 192 to 223. Class D 224 to 239. Class E 240 to 255. So by looking at the first octet value, you can identify to which class that particular IP address belongs to. And for the class A, B, C, the subnet mask is also given here, and total number of hosts, total number of networks possible. This is very important, total number of networks in class A, B, C, because in the earlier gate exams, you have got this question couple of times. So there is a possibility for that to get repeated in the BARC also. Okay. Along with IPv4 header format, please revise, go through this TCP segment format also. Here we have some 6 flags. 6 flags will be there. 1 bit fields will be there as PSH, URG, RST, ACK, FIN, and some other word, push, urgent data, reset, ACK, FIN, and what else? I am not getting it now. Urgent pointer, some other. Please revise that once. There will be 6 flags. 1-bit fields will be there. And what is the port address length? 16 bits. So here every field and its width is mentioned, guys. Yeah, SYN. Yeah. Thank you, Rahul. Yeah, it is SYN. So every field and its width is mentioned. So there is a possibility for asking the TCP segment format field width in the BARC exam, or there is a possibility to get a question on these flags. So to terminate the connection, FIN flag is set. To indicate that it is a acknowledgement segment, ACK flag is set. To indicate that it is a piggybacked segment, URG will be set, ACK will be set. And to indicate that the segment has to be forwarded to the next layer, that is application layer, PSH will be set. Like this, every flag has a specific purpose. So please do revise that purpose once. Okay. Even this TCP header also, if you just identify, its header length is also of 20 bytes to 60 bytes. Okay. Now we know the port address length is 16 bits. So with 16 bits, total 2 raised to 16 numbers, that is 65,536 port numbers are possible. These 65,536 port numbers are divided into 3 groups as well-known ports, registered ports, private or dynamic ports. So well-known port range is 0 to 1023, 1024 to 49151 we call as registered ports. Remaining are said to be private ports or dynamic ports. And for all the protocols, what port numbers are allocated? Well-known port numbers are allocated. So I am listing the popular protocols and their port numbers here. FTP data port number is 20, for FTP control 21, and secure socket this SSH has a 22. SMTP simple mail transfer protocol port number is 25, and we have a telnet for remote login service, its port number is 23. DNS, this is important, many times it is expected, the port number of DNS is 53. HTTP port number is very popular, I think well known for everybody, that is 80, and POP 109 and 110. So for POP, if it is just asked only POP, you can directly take 110, and for SSL it is 443, and for IMAP that is 143. Like this, please remember port numbers of these popular protocols, because there is a possibility of the question. Okay, so these are what very important you have to revise without fail in the computer networks before you go for the exam. Okay, now let's switch to programming and data structures, where you have very less formulae or important points, because mostly you will be given the program and you will be asked to trace in PDS, but still we can have some important points on arrays and pointers. That is, let's say A is array and P is a pointer, I be the index. Then for one dimensional array, when you say A of I or I of A, P of I or I of P, that gives value at index I. And when you say A plus I or I plus A, P plus I or I plus P, you will get address of A of I. In the same way, can we understand for two-dimensional array? No. For 2D array, it is little different, because 2D array is what? Group of 1D arrays. Right? So for two-dimensional array, when you say a plus I or even star of a plus I, because a plus I means it is the first ith row, even star of a plus I, value at that row is not single value. So you have a complete row. So when you say star of a plus I also, what do you get? Address of ith row. And when you say star of a plus I plus j, then what do you get? Address of ith row, jth column. And when you say star of a plus I plus j, then you will get value. So please remember this convention so that it would be easy for you to answer these questions or programs on arrays and pointers. Also, in GATE, we may not expect it, but in the BARC, there is a possibility for asking a question on address of an element from the arrays. So how you calculate the address? By default, address of x of I is b plus I into n, where b is base address. And what is I? Index. And what is n? Size of each element. So if nothing is mentioned, what you have to take? The default is indexing starts from 0. And for 2D arrays, if index starts from 0, we know 2D array is stored in two forms, RMO, CMO, row major order and column major order. Default, you can take this. Like if nothing is mentioned and is asking for the address of a particular element in the 2D array, you can take directly row major order as the reference. So how do you find address of x of ij? It is b plus I into c. What is c? Total number of columns. What is r? Total number of rows. And what is I? Row index here. And j is column index. So using this formula, you can calculate the address directly. Okay, so please do include it in your short notes for quick revision. Okay, then directly we can switch to data structures part. In the data structures, majorly where you have more formulae or where you have to focus much means trees. So in the trees we have some important points, like the number of nodes in a perfect binary tree at level L are 2 raised to L. If you start the numbering from 0, it would be 2 raised to L minus 1 if you start from 1. And the number of unlabeled binary trees that you can form with n nodes is given as 2n cn by n plus 1. And the number of labeled binary trees. Labeled means you have combinations again. So that is 2n cn by n plus 1 whole into n factorial. Actually, it's a nth catalog number. I think you might know 2n cn by n plus 1 is to find out nth catalog number, right? Guys, are you able to follow? Fine, if you can't, make a note quickly, because this PDF I will share in the Telegram group, so you can revise from the PDF also. Just make sure you know all these points or you are revising all these points once. Okay, and in trees we can find out the maximum height if you are given that there are capital N nodes as n minus 1. Where do you get maximum height? In the skewed binary tree, either left or right, you will get maximum height. and minimum height you can say as log n plus 1 with the ceil value whole minus 1. Where do you get minimum height? In the perfect binary tree. This can be reversed, like you can be given height and you may be asked for the minimum number of nodes and maximum number of nodes. Minimum number of nodes you will get again in the skewed binary tree. Maximum number of nodes you will get in the perfect binary tree. And if you are given that there are x leaf nodes, then exactly 2 children will be there for how many nodes? X minus 1. So the number of nodes with exactly 2 children will be x minus 1, where there are total x leaf nodes in that tree. Okay, so please do remember these formulae. Then let me take you to algorithms quick revision. In the algorithms, without fail, please revise learn master theorem, because there is very much possibility, high probability to get a question on the recurrence relation and ask to solve. If you know this master theorem, much time can be saved. So if you find the given recurrence relation of this form, where the n value is decreasing exponentially, then by comparing this a and b to the power k values, you can match under which case it falls under, and then you can just analyze the sub case, and directly you can make a note of you can give the time complexity for the given recurrence relation. Okay, and this is for dividing functions. And for decreasing functions, if you find a master theorem which is of this form, then based on the a value you can directly give what is the time complexity. So all dear students, I recommend everybody, whoever are preparing for the BARC exam or any competitive exam where you have master algorithms in the syllabus, definitely go through the master theorem once. And then time complexities, we know different time complexities are termed as, if it is big O of 1, we say it as constant time complexity, log n, logarithmic, log square n, log square time complexity, n you say as linear, n square, n cube, n power 4, all those we can call as polynomial. This you can say as polynomial time complexity. And n to the power, yeah, of course it is given, yeah, okay. And 2 power n, you call it as exponential time complexity. And n factorial also you will have, n factorial. So which is more means this is less, and then you can take n factorial, that is high. Okay, because based on this you may be asked to arrange in the ascending order, descending order. You might be given some different time complexities and you may be asked to arrange in the order. So for that this can be useful. And we have different searching algorithms. Of course, linear search, binary search, BFS, DFS are popular, but we do have several other types of searching algorithms. At least you please remember these 4 searching algorithms time complexities. Okay, linear search, n, binary search, log n, depth first and breadth first, it is a big O of v plus e, where v is vertices, e is number of edges in the graph. And for sorting algorithms, I have mentioned the most popular sorting algorithms, not all. The time complexities are given, so definitely you are supposed to remember the time complexities. Heap sort, merge sort has n log n time complexity in all the cases. quicksort has n log n in best and average, but in the worst case, its time complexity is different. So that is the most popularly asked one. In the same way, please go through the time complexities of other algorithms also in in all the three cases. And in the sorting algorithms, we have a category called stable sorting algorithm, unstable sorting algorithm. For you to easily remember, I'll give one simple code for stable sorting algorithm, that is IBM, for unstable sorting algorithm, that is SHQ. What is IBM here? I means insertion sort, B means bubble sort, M means merge sort. These three we call as stable sorting algorithms. Selection sort, heap sort, quick sort, these three are under unstable sorting algorithms. There is a possibility to have a question on this also. Okay. And in these, merge sort is considered to be external sorting algorithm, sometimes heap also, but the other are always internal sorting algorithms or in place sorting algorithms. And here I have presented the time complexities of all the data structures, most popular operations here. Please go through these time complexities once. So I have reduced your work, guys. I only have consolidated all required and kept in this. So before you go for the exam, please keep this in your short notes and revise without fail. Okay, there can be a direct question on this. And we have algorithm design techniques, popularly dynamic programming, greedy method, backtracking, divide and conquer, branch and bound. Popular are DP, greedy, and divide and conquer. So I have brought some popular applications of each algorithm design technique along with their time complexity. So quickly go through this and try to remember the time complexities, because you can get a direct question you can get in the BARC, like matrix chain multiplication. Time complexity of MCM is dash under DP, or OBST has so and so dash time complexity, or Bellman-Ford algorithm. You can get a match the following kind of question. One side you can have all different applications, other side time complexities. You might need to match. Like that, there is a possibility, huge possibility is there in the BARC. So without fail, please go through the DP application, greedy application. So here I have presented greedy applications, main important algorithms along with their time complexities. Similarly, divide and conquer applications also. Okay, guys, these are very important. These algorithm applications, time complexities. Okay. Also, I have kept recurrence relations for some popular algorithms, because sometimes it is also asked. The recurrence relation of quicksort in the best and average case is 2t n by t plus big O of n. And in the worst case, it is t of n minus 1 plus big O of 1. Similarly, for merge sort, binary search, binary tree traversal, I have kept the recurrence relations also for your reference. Okay. So that's all with respect to computer networks, programming data structures, algorithms, these three subjects from my side. So I believe this formula revision session. In this, I believe you have got around 8 to 9 subjects formula revision or important points revision. So majorly, if you refer these, you will be able to pass through the cutoff, and also you will be able to stand in the top 100 or top 500 list. Along with this, please do refer DBMS, other subjects which we are unable to do in this session. You do a self preparation of the other subjects also. Okay, so I hope this session helped you in revising important points for computer science BARC aspirants. Guys, keep liking the session, keep sharing the session before you leave. That's all for today from my side. See you in the upcoming practice sessions. Subject-wise practice sessions will be held, and the detailed schedule will be shared to you very soon. Okay. Thank you so much for joining the session. Keep attending the sessions regularly. Keep learning. Keep growing. Thank you, guys. See you in the next session. Till then, have a great time. Take care. Bye bye.